Good. So welcome to the next slot, and welcome in Zurich and also in Canada. This tutorial that we are giving here will be much more on tools than on anatomy. So Nicola was the real expert in anatomy. I'm not. I'm a computer scientist. My name is Timo Dickscheid, and I will introduce you to the Siibra tool suite, which is a set of tools to work with our multi-level brain atlas, and which of course includes the big brain model and data that we have linked to the big brain model. So we will show you how you can access this and how things are organized. And they will, different from tutorials that we did in earlier Winterschools here, we will put more focus in this round here on using the Python client. This is a newer development than the 3D viewer, which you will also see. And there was a lot happening in the last year, 1.5 years, and it has now so many functions that we thought it is time to focus a bit on it. And we also saw in our last high-level meeting in Croatia, we also saw that there's quite an interest in that. So this will definitely be a focus today. And so before I start, it would be interesting to hear so who's already familiar with Python? Just that I have an impression. Okay, good. And who never did anything with Python? And of those, did you program in MATLAB or something, or are you completely new to programming? Okay, it's okay. So what we will do will be easy in terms of programming, but of course it will be programming to some degree. So it might be a bit tricky for you, but we have people here whom I will introduce in a second who are also around to help you out. And most of the stuff I will anyway show you, and you don't have to do it yourself. All right. Before we go ahead, I am sorry I missed to put photos here. I planned this in the morning. So who is supporting us? Well, I will give the presentation and guide you through everything. But we have also Xiao Gui here in the back, who is the main developer of Siibra Explorer, the 3D viewer, but he's also very familiar with the Python client. And we have Ahmed Cimcek here, who is rather new to the team and who helps in the development of Siibra Python. And they will, on the Yiddish side, be here to walk around and help you out. But the people in Canada just ask questions and raise your voice. I must admit, at the moment, I don't see you here with all these devices, but I'm pretty sure I hear you. So if something is going too quick or you have questions, just raise your voice, yeah, and I will stop and help out. And we have plenty of time, so we can go slow and ask questions. And I also didn't plan this very strictly, so this will be a rather free-floating presentation. So please ask questions. It's all about interaction, this one. Yeah. All right. So the goals today is I will take a few slides, but really not many, to introduce you a bit to the conceptual ideas behind this multi-level human brain atlas. And I think this overlaps also with what Nicola has explained in much more detail. I think we can be brief here, but I will take maybe some 10 minutes with a few slides to explain a bit the basics. And then to get some intuition, we will go into the web viewer where we have this atlas available for interactive exploration. That is where you usually can easily understand what's there, see it, rotate it, click it, and so on. But that's, of course, not the right tool if you want to do a reproducible data analysis or things like this. And so the main part, you see the big arrow here, the main part is definitely then that you learn how to access different functionalities, contents, concepts of the atlas in Python. We will do this step by step, and you will see many things, not all of them. But I hope, so my goal is that you understand what is the scope of the Python client, how can I find basic things, where can I find documentation, and you have sufficient knowledge to get started yourself with more advanced things. So this will here definitely be the main part. We will start with Python programming only in, let's say, 20 to 30 minutes. But I would anyways like those who have a laptop with them and want to do some programming to launch this Python notebook now, because then we save some time later on, since it's so we will be running Python in the cloud, and the system had to generate for you a container with the software, and also we will just launch a few lines of code so that already some data is loaded in the background. But we will not discuss Python now. So those of you who want to follow online, just type the link on top, the GitHub link in your browser, and then wait. When you're on the page, there is here a little button where you can select a branch of the software. And in this, if you click on this button here, you will find a branch that's called Winterschool or something like that. Please use that, please switch to the Winterschool. Otherwise, you find here other tutorials that we are not doing today. For now, I will explain how all that works later on. What I would just ask you is, you see here on the top, a run button, yeah? And if you could just run the first two cells. So if you press the run, it will here, it goes from cell to cell. In the first cell, it will install the software. And in the second cell, it will already import some packages and instantiate a few things. I will explain that later, but you just run this cell up until you see this part one here. That's where we stop. Yeah? And then you can just leave it. Yeah? I just wanted to do that now, so it has already loaded a few data sets when we go ahead. Yeah? So we want to go to these three things. Let's first talk a little bit about the conceptual ideas. This whole framework is built around the digital brain atlas. And when we talk about digital brain atlas, we usually think about three main ingredients. The first one is that we have a definition of the brain structures. Yeah. So basically the names and the definitions of brain regions, and typically this is a hierarchy. This is typically a hierarchical tree of regions. What you see here is a print out of part of the tree of our cytoarchitectonic unit brain atlas. But this is of course just semantics, these are just names, right? At this place. What we then also need is a reference brain space, which actually defines a 3D coordinate system, just as we would have a 3D coordinate system of the Earth. And third, we would then delineate the structures that we have defined in the parcellation definition on the left, delineate these structures in one of those reference brain spaces, which then actually gives us a parcellation map. Yeah. So these are the three main things that we see in an atlas: names of brain structures, a reference space, and parcellation maps that actually tell us where the structures are in this brain reference space. We always talk about the multi-level atlas here, and this multi-level concept means different things. It mostly means that we assume that we don't just have one type of parcellation maps in the brain, but different ones. Yeah, so we can map the brain in terms of its cytoarchitecture. We could map it in terms of its fiber architecture or functional aspects. So there are different ways that we can map a brain, and this gives rise already to multiple levels in such an atlas if we combine multiple parcellation schemes. But more importantly, even in the system that we will be looking at, we are also supporting multiple reference spaces. So we assume that even if we have one parcellation, let's just think about the cytoarchitectonic maps. We assume that we have these cytoarchitectonic maps delineated in different reference spaces. For example, in the M&I space, which is very common in the big brain, yeah, or maybe in the free surface. Yeah. And these three things would be different maps, but they would be maps of the same parcellation, right? So if we deal with multiple reference spaces, the concept of a parcellation is not exactly the same as the concept of a parcellation map. We can have one parcellation and we have maps of that parcellation in different spaces. Yeah? And these are, of course, different maps, but they are mapping the same brain structure. And that is already a key part of the system that I am showing you. So the system has multiple reference spaces at different spatial resolutions. It has different parcellation schemes and different modalities. On top of this, the idea is that we use this system to link multimodal data to the brain structure, so that we not only provide maps of brain structures, but that we also use this framework as a reference to link data sets with regional specificity or with whole brain relationships. But the idea is we are linking data and measurements to the brain, to different structures in the brain, and make them accessible via these parcellation maps and via their locations in reference spaces. That's the idea, and that's also what this image should show. So we assume that we have brain regions, and from there we can see the variability of such brain regions across the population. We can go to higher resolutions across the scale. For example, here we can see that same brain region in the big brain at much higher resolution with much more detail, and we can zoom in to the level of individual cells. Nicola has shown these things in her talk, but we haven't discussed how you can access such things. Yeah? How can you actually get there? How do you find the zoomed in detail of the histological section for a brain region yourself without asking Nicola? And that's what we will be talking about today. Yeah. So the system allows this. You can fetch a parcellation map. You can look at individual regions and their properties. You can look at the location of that region in the big brain, and this way navigate across the spatial scales. And then you also have different modalities. So this means you can choose different parcellations, and you can also choose data sets that reflect different forms of brain organization. And these data sets could be linked to brain regions. They could be linked to locations in the reference space, the coordinates, or they could refer to a parcellation or to a whole brain. So just to give you a few examples, such a data set could be, let's say, a whole brain model of fiber orientations from DDI, for example. In that case, it would be a data feature that is linked to a whole brain, right, in some reference space. It could be a density of neurotransmitter receptors measured in a certain brain region. I think Nicola has shown such examples. In that case, it's a data set that is linked to a particular region. Yeah? Nicola has released such data sets and assigned them to cytoarchitectonic brain regions. And then we have a data set that is linked to the name of a brain structure. Yeah? And since we have a map of that brain structure, for example, the big brain, we would also know where it belongs. Yeah? Another example is, for example, a connectivity matrix that has been extracted from a neuroimaging cohort. Yeah, and has been grouped onto a certain parcellation. Yeah, then we have a data set that refers to complete parcellation, since it knows the connectivity profile for each of the regions in that parcellation. Yeah? So these are different modalities, different data sets that are in some way related to this reference framework, either in terms of locations or brain structures. Yeah? This is what we see here on the top. And the tool suite that you will be seeing now gives you access to such things in a very easy and streamlined fashion, without you having to Google and download things. That's the main idea. Yeah? And we will go through this in detail. I will very often use the Jülich brain cytoarchitectonic atlas to go through these things. And I guess that Nicola talked a lot about this already. So you know that it delineates cytoarchitecture and these differences in the arrangement of the cells. So I'm not going into detail about this anymore. I think you have also, you're also aware after Nicola's talk that the atlas has mapped such regions in different postmodern brains and then aggregated the region maps into probability maps. I'm not sure if Nicola talked about this, Yeah? But the Jülich Brain Atlas contains probability maps that have been aggregated in the MNI space from detailed maps in different postmodern brains. So these show us basically for each structure in the atlas, and there are around 300 structures. It shows us in the MNI reference space what the variance of this brain region was as it was observed in 10 different postmodern brains. Yeah. So this is a probability map, and the red values here for one region. This is the frontal pole, and in this visualization, red tells us at these locations we have observed this map in all the 10 postmodern brains. Yeah. And where you see blue, it means only in maybe 1 or 2 of the postmodern brains did this area extend so far from the center. Yeah. So these probability maps mean we have for each structure one map. All right. The system that you will be seeing uses a lot of data, and all of the data that's in the system is actually a publicly shared data set. Yeah, there might be 1 or 2 exceptions of pre-release data, but usually everything you see, the maps, the reference templates, the reference spaces, these linked multimodal features and so on, these are usually all publicly available data sets that you could also find for yourself independently. The system integrates them. Yeah, so we have these data sets stored in eBrains. That's the research infrastructure we are building with the Human Brain Project here in Europe. And these data sets are stored in this infrastructure on large storage systems. And there's also a metadata database, what we call the knowledge graph, which contains metadata. And that's where we store the things. This Atlas framework then sits on top. It knows about all these data sets, and it can actually also detect new ones automatically and brings them into this context, which I just talked about. So it basically reveals for you the links between these data sets in terms of anatomy. And the way you access it is in different forms. The most obvious way is an online viewer, which we will look at now. Yeah? But then we have this Siibra Python client, which also allows you to access it. That's what we will be doing today. So let's just, I think that's from my side enough concept. You would see it live anyway. So I don't want to talk so much conceptually, but if you have questions, just ask. Let's have a look at this online viewer. Those of you who have a laptop, you can just go to this online viewer by, again, writing the link here, atlases.ebrains.eu/viewer. When you do this, you will not yet see a viewer. You see a selection of different atlases where you should just select the human atlas. And then you should see a screen that is similar to the one here on the slide. So I continue. We were trying to get some intuition. So here in the viewer, we see one postulation now in the MNI space. And this postulation gives us rise to a set of structures. And these structures, you can find them here in the top left. There's a little icon here, and if you click on that icon, you can actually see the hierarchical tree of the brain structures, and you can search to them. For example, I can search for V1, and then I see here where V1 is mapped and how V1 is called in this section. And I can click on one of the structures, and what then happens is that the system selects this brain region, and if it is a probabilistic atlas, which provides a probability map, it will also automatically load the probability map for that particular region when I select one. That's not the case for all the postulations we have, but in this case here you see now such a probability map. You see a side panel. I will get to this in a minute, and we can disable this selection by clicking the X here in the side panel. But we also see the selection here in the bottom overview. So if you look here from the left to right, we are currently in the human atlas in the MNI space. We are using the Jülich Brain cytoarbitrary maps in version 2.9. The version 3 is, by the way, coming very soon. And we have selected one region, that's HFP1. I can X that away, and then I have to back the whole oscillation again with me. Yeah. So what we can do now is we can switch reference spaces. So if we click the M&I space here on the bottom, we can also change to the Collins space. We can change to the big brain. We can also change to the FS average surface space. I'm doing that here just for the moment. The surface space uses a bit of a different viewer since it has no voxels. It just has surfaces, but it functions in the same way. I can click a region here and the side panel opens, and I can deselect it again, and so on and so forth. For the free surface space, I can also on the bottom right choose different flavors. The white matter surface, for example. Just take a little bit. Here we go. Yeah, but if you click again here on FS average, this is where we could switch to big brain. Yeah, so here you can also select the big brain. Then the viewer will change color a bit because the big brain is better visualized with a bright background. And in the big brain, you already see here, we have also some slightly architectural regions mapped. We are continuously adding maps, detailed maps of the newly developed data in big brain. And here, if you use the scroll wheel, or on the Mac, it's 2 fingers on any of those views, you can then zoom in. So I'm going here to cortical position, and then I just use the scroll wheel to zoom in. And this will then load the template at higher resolutions. This might be, if you're on Wi-Fi, it might take a bit. And I've also heard that in Canada it's slower. So we are thinking about mirroring the data in Canada. So here it somewhat works nice. So if I zoom in, it's fairly okay. Yeah, you see here's already the high resolutions. But it might not be that fast on each computer, each network connection, each location, and so on. Yeah. As I said, it's not the main intention to discuss the viewer today, but you could also use this to choose different cutting angles. So if you press Shift key, and then you click and drag with the mouse in one of those views, you can actually rotate. You can rotate the section here. Yeah? So you can choose different cutting angles here at the full resolution. You see it here. So yeah. So you just press Shift, and then you click in the view, and while you keep clicking, you move around with the mouse. Yeah. Please be aware this 3D view here on the bottom right, it does not provide a full resolution. This is just an overview. Yeah? So the full resolution information is in these sections. Yeah? Good, but it's not our main the main point. So we will return to the viewer for a few other things, but for the moment, I just wanted to use this to get this habituation. If you click here on the parcellation chip here on the bottom, many of the parcellations we support here are not mapped in big brain. So of course, we don't have a native map of functional activations in big brain. But what you can use in big brain is the cortical layer parcellation you find here. That's the parcellation of Konrad Wachstil and colleagues. So this is mapped right away in big brain. And if you select this, you see here the map of the different cortical layers. This usually takes a bit to load because it has a number of quite high resolution surface meshes. But you can see these cortical layer maps. I think that you could also add in the slides. Okay, that's should. No, one more thing I wanted to show. So I'm just returning to my slides for a second. So we have seen in the viewer there are parcellations and regions. There are reference spaces, and these two can be combined to see maps in different reference spaces. Yeah. What we didn't discuss yet are these multimodal features, and we didn't yet look at that. But you can find such multimodal features also in the viewer. So for this, I go back to the here to the Saito architecture, Unity Brain version 2.9, and I also for simplicity, I also go back to the MNI space with lower resolution here. You see when we switch around between reference spaces, the system preserves the view, right? So I was zoomed in the big brain, then I switched to the MNI space, and it has also this oblique rotation and zooming level, although it's a different space. Yeah, this works because Siibra in the background is aware of the relationships between the reference spaces. So it knows the nonlinear transformations between the reference spaces and it uses that. Yeah? So as you switch the reference space, it transforms the current view into the other reference space and tries to preserve it as good as it can. Yeah? You can always return to the default orientation here on the top. You see here on the top where the coordinate is written. If you can open this this little dialog here, and there's in the top row there's a possibility to reset the rotation and the zoom here with these three icons. So that's how you can always easily return to the default view. One thing that you should maybe just know is the current view is encoded in the URL. So as you move around and zoom in and so on, if you copy the URL, this gives you this exact view. So you can change, you can share it with colleagues via email, and when they launch the URL, they will see the same thing that you are seeing, right? So it is typically a long URL, but it encodes it. And if you really like something you see, if you found a structure in the big brain or something like that, you could also use this here. There's also a little icon here that's where you can create a custom URL. So something like these tiny URL things. If you are authenticated via eBrain. So when I want to use this, it asks me to authenticate, but then I could even give my view a name and create a permanent link. We are not doing that now. It's just the information. I promised that we talk about features as well. And here in the viewer, you get access to features by selecting a brain region. That's how it's currently solved. So if I click here on area HOC1, the primary visual cortex, I click it to the left hemisphere here. The side panel opens again. And in the side panel, you do see a description, but you also get a list of regional features. See that here on the left? Mm-hmm. And some of those features are labeled with a little color. These are features which are supported by the viewer. Besides just showing you the data set that is linked, it also supports this feature. So this receptor density, if you click on it, the side panel opens, and you even see the fingerprint of this receptor density in this brain region. Yeah? So we see now here this data set. Density measurements of different receptors for HMC1, that's the area we selected. We see a description, and we see here this fingerprint with the different neurotransmitter receptors and their mean and standard deviations. And we can even click on one of them. It shows here NMDA, and it shows me a sample cortical profile of this density. Yeah. You will not find these neurotransmitter densities for each brain region. There are currently, I think, the data set that is public has, I think, 40 brain regions, and for this 40 brain regions, you find it. For others, you will not find neurotransmitter receptor density. Of course, we are working to include more and more data. Yeah. So this is the way that you find these multimodal data features. In a few minutes, we will see how that works in Python. And there you can do that in a reproducible way. But here you can already download data sets. So you see here you can download the TSV file that contains the actual values. And what you also see on the top of the side panel is that this is a data set in eBrains. And there is a little icon here. I don't know what the name of that icon is. You always find that in apps that tells you take this somewhere else. Yeah? So if I click that, you will see the corresponding data sets in the eBrains knowledge graph. Yeah. So when I click here, we will actually see the published data set from Nicola in the eBrains knowledge graph with a lot more metadata, right? So here you see really the description, the authors, the license. You can also get access to these CSV files here. Yeah. So this is really the data set page for that data set. Publications. So you see here a whole lot of information. And this is the eBrain's knowledge graph. This is the web front end to the eBrain's knowledge graph. And Siibra will talk more about the eBrain's knowledge graph tomorrow. This here is just to let you know, most of what you find in the Atlas is actually a data set in eBrain's knowledge graph. And Siibra has in the background the links. Yeah? But the idea in the Siibra toolkit is to focus on working with the anatomy, not to focus on the data sets. But it is linked. Good. There are also other features which are not specifically supported, but they are also, like I just fetched one randomly here. These are still eBrain's data sets, and you can still open and download them. Yeah? It just means that the viewer doesn't give any specific support to work with this particular data. It only has a link. There is an additional panel for connectivity, and here you find access to some connectivity matrices from eBrains that have been computed for the unit-frame oscillation. So once you select this connectivity panel, it colors the brain regions by connection strength to the currently selected brain region. Yeah, we still have region V1 selected here. So we see a color map that shows us connection strength with V1 in the left hemisphere currently. Yeah, you also see the connection profile here as a color bars. You can switch between lock, scale, coloring, and not. And you also see that this is just one subject from the HCP cohort, and what we are seeing here are streamline counts. And we can also change this to other subjects. So we currently have here, I think this data set has 200 subjects from the HCP cohort, or is it even more? Yeah, 200 subjects, which are pseudonymized, so we don't know their names or anything. But you can here look at different subjects. You can download also this connectivity matrix as a data file, and you can also switch to streamline lengths. You can also switch to different cohorts. So I think for streamline counts, we also have here data from our 1000 brains cohort, different connectivity matrices from different neuroimaging cohorts. Yeah. So you can browse connectivity matrices that have been computed on this oscillation. Good. These were a few regional features. Yeah. As I said, we look at the viewer only to get some intuition, not to learn everything. We will look in more detail in Python how it comes away. Do you have any questions at this stage? So my aim is that at this stage you have an understanding that we use different coordinate spaces. With the big brain, there's even one at the micrometer level. We have different oscillations, and we have all sorts of data linked to these brain structures and brain locations. Now that's the main thing you should have understood at this point. Okay.
Question.
Yeah.
Can we search in any way with words? So, for example, motor cortex, left side, or something like that?
Yeah. So you can search for words, but not for functional concepts. There's actually something I requested from some of your working group. If we could tag the site of regions with some easy, maybe that if you would put auditory, for example, yeah, that's currently not the case, but you can of course search for names. Yeah, so if I go here, I can search for, I know the motor cortex is for P or for A, so this works here, yeah, of course. But if I search for motor, and if I write it correctly, it doesn't find the brain region, right? So this is something we currently don't have because simply this oscillation is not tagged with such terms. No? Yeah. I think it's interesting that you asked because I requested this as well.
I don't know the name of it.
Yeah. So this is something that's not good. What you could of course do is you could switch to different oscillation surveys in the functional terms. You could switch here to the oscillation that is based on function. This is this atlas of functional modes from Bertrand Paris. And here you might probably have more luck if you search for functional terms, right? Actually, I've never tried this. Yeah, but These are the regions from the function atlas from Bertrand, but they also not checked the functional terms. So this is something we don't have in here. And this would require a neuroanatomist or a neuroscientist to actually provide these tags, right? They currently are not part of the atlas definition inside the sensors, we don't have that. Okay. Then let's start doing Python and see how these concepts are reflected in how we try to transfer these ideas and this way of working with the system into programming. So if you go back to the now you can go back to this notebook, and I will use my local version of this notebook here. So that at least I'm not dependent on the web connection. So mine is running locally, but yours is running in the cloud. And at this stage, you should be here somewhere here at the point where we have written part 1. Before we start, since not everybody is familiar with these notebooks, I guess, just a few very little words about this. These Python notebooks are, so to say, it is in simple words a web page, which is organized into a sequence of cells, as you have seen. You can execute these cells. And there are mostly 2 types of cells. One type is it has text, and if you execute it, it just shows the text in a nicer way. That's what we have on the first cell. Or it is a cell with programming code in Python. And of course, then when you execute it, it executes the commands in there, right? So the idea in these notebooks is that you can mix documentation with execution of programming code. Yeah, that's what we will be doing here. And you can always hit this play button to execute the current cell and move on to the next cell. I'm typically using Shift Enter. It does the same thing. So if you hold Shift and press Enter, and then you press 10 times Enter, then you will execute 10 cells and you will enter the 11th one, for example. And you can always click into a cell to edit it. So let me just go back. So in this case here, where we are starting, where we use read part 1, this is a cell with text. If I double click or single click into this cell, you see here actually the text, and I could edit it. Yeah? So I could write here, hey, hello. And then I can execute this cell, and then I see the text with hey, hello. Right? The next cell is really Python code. And this has a single line of Python code in that case. It imports the Siibra package. Yeah? And that's what we should be doing now. We execute it, and then the system loads Siibra. If you're doing this for the first time, it takes a little, but most of you have done it before I started my presentation, so it should be quick and you don't see any outputs. But if you do it the very first time, it takes a little bit because Siibra then loads all its configuration details and so on. The second time you do it, even if you shut your computer down in between, is already faster because it builds a cache on your computer or in the cloud system that you're using, and it will not always fetch everything from the web. So the more you use it, the more stuff you have in your cache, the faster it gets. Yeah? If you use it for the very first time, it may take a bit because the software itself doesn't have any data, and it fetches it piece by piece. The main idea in the software is that we do what we call lazy fetching. So it requests data, information from online resources once you use them the first time. Otherwise, you would download all the stuff when you import Siibra, and that would not be feasible. Yeah? In particular, for the big brain, you would not want to download the big brain only to use Siibra. So it is lazy. It will download things when it needs them. And if they are not that huge, it will cache them on your computer. Some things it will not cache, like it will never cache the 1 terabyte big brain volume on your computer, of course. Good. So the first thing I wanted to show you is mostly what we did in the viewer by clicking on parcellations, finding regions, finding reference places. We have to do that as well in programming. So we have to find out which parcellations do you have, which reference spaces do you have, what are their names, how can I access them. This we are doing in Siibra what we call instance tables. So Siibra provides kind of tables. These are the variables that show you what it knows, what it has in terms of pre-configured objects. One of those is Siibra.parcellations. So here the next cell that I'm executing is Siibra.parcellations. When I execute it, it just tells me what that is. This is an instance table. Yeah. So it holds instances of certain objects. And if I print this thing, it actually shows me which objects it has. Yeah. So you see here, we have quite a few parcellations in here. They are not all even from the human atlas, there are also some from mouse and so on. But you also see that we have here this our unit brain site maps in different words and so on. Important information is these are just the ones that we have pre-configured. So Siibra can at any time be extended with other ones, and you can even add your own ones. This will not be covered today, but you're not limited to working with those. This is what Siibra brings you off the shelf. Yeah? And this is also being extended constantly. So this just shows me which parcellation objects Siibra has. But if I want to have one such instance to work with it, there are different ways to do that. And if you are in an interactive viewer like this one, I'm here just opening a new cell. It's actually quite easy because you can use tab completion. So you can just write Siibra dot and then use tab. Okay, this is, and I write, for example, parcellations, PAR, I press tab, and that's parcellations, dot, and then I press tab, and it shows me these instances. So I can here, just, for example, type JU Jülich, I just select version 9, and then I execute the cell, and then I have access to the object that represents the unit brain parcellation. Yeah? And these instance tables all work the same way. We also have instance tables for reference spaces. For atlases, we are not talking about atlases as such at the moment, and also for a few other things. Yes, so you can also do it in different ways. So you can also, behind the instance table, write get. This is a function, and then you can put some keywords in there. This is especially easier if you don't have an interactive interpreter like here, where you have this auto completion. Yeah. So if I, for example, say long bundles, it will only for these words, it will figure out that it must be this one here, right? Let's say get long bundles. I get the fiber bundle parcellation, and I can also use this square brackets to do the same thing. Yeah. The next cell here is empty. And you can use that yourself to just try to access the M&I reference space. I can tell you that it's also written a bit above. You see that here, the reference spaces, the instance table for this reference space is called Siibra.spaces, as you would expect. Yeah. So just try it yourself and just try to access the M&I reference space, which should be a single line for you to write. You can also access the big frame reference space. It will not load any data at this stage. As I told you, Siibra is lazy. Yeah, so if you use big frame, it will not load any data. It just gives you the object that represents this space, but it doesn't load any image data until you really need it. So anyone got it already? Yeah. Okay. So what did you type?
You write something for me.
Siibra spaces. And then I use the tab completion as here, and this is the M&I one here. Yeah. And you see what you get is a space. I will be talking about what these objects mean. But for now, this is just a small type, a small object in Python that represents this space. It knows about that space, not much more. Yeah. So, for example, this space has some properties. For example, it has description, I guess. Yeah. So I can ask it for the description and a few more things. But it's very small, lightweight thing. It's more or less just a name. Good. I think I will move on. So these parcellations have properties. Yeah, for example, if I fetch here in the next cell the unit frame parcellation, it has a description and it has publications linked. You see that here. It also has some links to the knowledge graph, which we are not looking at the moment. But the most important thing, of course, is the parcellation gives us the set and the tree of all these regions that we have defined, right? That's the most important thing. So by requesting the uniform parcellation, we basically have access to the region tree, and we know which regions are known in this concept uniform. And in the next section, we are looking at this. So to get a visual representation, there's actually a function of each parcellation that's called tree to string, which we could just print, and then it actually prints a textual representation of the whole tree. This is just for visualization purposes, of course, but it's an easy way to get a quick look at how many structures it has. The interesting thing is in Siibra, a parcellation is in fact actually just a spectral region. It's the top node region of a region tree of the parcellation. And it has a bit more metadata than the normal region, but it is in fact actually also a region. And any region in the tree is a similar thing. Yeah? So is, for example, here the Basel IV brain, it would also be a region object, and it has the subtree under itself, knows about all the regions that are linked under itself. Yeah? So these are all region objects. And we can directly get access to these region objects by searching for keywords, similar as we did in the viewer. So I can tell the parcellation unit frame, give me the region that's called amygdala. By calling this function get region, I'm actually saying what I specify now should resolve to one exact region. So if that's not the case, I will get an error. Yeah? If I write here a name that does not translate into a single region because it's redundant or unknown, I will get an error. This function assumes what I provide, it doesn't have to be the exact name, but it has to match exactly to one of the names. And amygdala does. So if I search for amygdala here and I print the tree representation of amygdala, I get exactly the subtree that is organized under amygdala. This is still not a leaf region in the atlas, so there is not a map for the amygdala as such. Yeah, it's a parent object of other ones. And each of these regional objects have a lot of functions. Just to show you a simple example, one function is you can compute the centroids of such regions. But to compute the centroids, since we are using multiple reference spaces, we have to tell Siibra in which space do you want me to compute the centroids, right? Do you want the centroids in the MNI space? Do you want the centroids in the big brain space? What do you want? So when I want to compute centroids, I have to tell Siibra in which space. Here I do it in the MNI space. This takes a little bit because at this point it has to fetch actually the map. What it's now doing is it actually downloads the map of unit brain and uses this to compute these centroids. And the centroids as such is a structure of points. So if you look at this, it is a point set. So Siibra has different data types. This is a point set data type. And it knows, these points know where they belong to. So I can say centroids.space, and Siibra knows the name. So Siibra knows that these points belong into this reference space, right? If I would have computed the points in a different space, they would also be checked with a different space. And this is very important. So one of the main ideas behind Siibra is it tries to make things safe. It tries to avoid that you confuse coordinate systems, reference spaces, names of regions, by really knowing what things are. Yeah? If you would program this yourself, this is typically what goes wrong. Yeah, you store a coordinate in as a number, yeah, and then you use it later on in your software, and you typically forget, was it given in millimeters or in voxels? Was it actually the column space or the MNI space, or what was it? And then things go wrong because you don't see that with the numbers. In Siibra, that's safe. Yeah, I compute centroids, I get point objects, and these point objects know in which space they belong. Yeah, I cannot confuse that. If I use these points later on in Siibra will check. So if I want to use these points to do something in the column space, Siibra will know this point is not in the column space. It will actually transform this point into the column space, or it will complain. Yeah? But it tries to make things safe that you don't do errors. And this is a very common error. All right, and we can plot these points. This is just a function from the popular Nylern library. It's only just formalization. Okay. Until this point, I admit that this is quite boring, right? What we were looking at now, it's more or less just names of things. These were just names of spaces, names of population, names of regions. That's not terribly useful. Yeah? This is just semantic stuff. Of course, you're more interested in what is actually the oscillation map, what is the image, what is the volume, and these things. And that's what we will be doing next. Yeah? This is the part 2. So what we are doing here now is we download the maximum probability map of the Jülich frame, and this is a 2-step process. You can do it in one, but in order to understand it, we do it in 2 steps. We first, don't be confused by the brackets. That's okay. But actually, I just access the oscillation again, and I think we have done this anyway with few cells fast. So this Jülich frame here is just a oscillation. That's not a map. In order to get a map, I have to tell Siibra in which space I'm interested to get that map, right? So the next line is actually saying, Jülich frame, give me a map of yourself in this space. And I'm here again using the MNI 152 space. I could also use another one. Yeah? And this gives me actually a map. I told you that Siibra is lazy. So I have not the information about the map. I still haven't downloaded it. Yeah? So Jülich MPM is an object that knows about the image data. It knows where the image data is. It knows all sorts of stuff, but it has not loaded yet the image data because I haven't used it yet. In order to use it, I actually can fetch the image data, and then it will load it. So the actual image, if I fetch from the NPM, then I get a nifty image. And that's an object that you know. Nifty image is really, that's a structure now. It has the voxels, there's the array, it has an affine transformation matrix, and so on and so forth. And this is something you can use right away in Python. So nifty images are objects that are very common in Python workflows, and you can use them with all sorts of libraries. The example that we have here is we use the Nylern plotting library just to plot it. And this is here more or less a single line that we can plot it. An interesting point is now, since we have this extra step, we have the parcellation map in MNI space, and we fetch. By fetching, we download the whole map, but I can provide arguments to fetch. I can, for example, tell the fetch method, I'm only interested to fetch from this parcellation map the mask of one region, yeah, which comes from the same volume actually. So that's what we do here further below. I use the same thing, Jülich MPM, and fetch, but now I tell it I want to fetch region 4A lab. Yeah? I don't want to fetch the complete parcellation object, just that region. And then when I plot this, I really get just the mass of this particular region. Yeah? But I'm fetching from the same thing. I have the Jülich frame map in MNI 152, and I fetch 2 different things from it. Complete map and the mask of a region. So this works the same way. Now we have also seen probability maps. And probability maps are a little bit different from those, but everything works the same way. So if I want to have the probability map, I take the parcellation object, request a map in a particular space. That's the same thing we just did. Nothing different. The only difference is that I now request a different type of the map. I request a statistical map. Yeah. And this will then give me the probability maps. And from these probability maps, I can do the same thing. I fetch and provide a region name, and then I get a probability. I get a nifty image with this probability map. Here we go. So from here on, things will very often be the same. Yeah. So things will be very similar. If you want to do this with big brain, the commands are more or less the same. We will do this in a few minutes, not right away. If we want to work with surfaces, it also works the same way. Again, we have the parcellation, Jülich-Brain. Again, we ask Jülich-Brain to get a map, but now we provide a different space. Yeah, we want to get a map in the FS average space, and that's actually not a nifty image, that will be a map. Because this is a surface. Yeah. So if I fetch from this map, what I actually get is not a nifty image. I get a structure that has vertices and faces and so on, because that is a surface. This is not an array of objects. This is a surface. But the commands are just the same as you see here. And I can also easily feed this into common tools. This is again here the plotting library of Neider. That's a library that we have not developed. It's a very common library in neuroscience. That's not from us, that's from I think mostly developed in Paris as well. And we can use this here to plot the surface. Yeah? This is also a very simple and common data structure for the surfaces. Okay. So the next cell is empty. If you like, just use it and try to load the Difumo 64 map in MNI 152 space yourself. Difumo is this functional map that we saw earlier. Just to remind you about the steps, you would first access the parcellation, the Difumo parcellation. Then you would ask it to fetch, you would ask for the map of this parcellation in a certain space, and then you fetch to get the image object. You might probably wonder why they have these two steps, right? So if you say get map, why don't you get the image object right away? Yeah? Why do we have this extra step in fetching? And the main reason is that we will also work with high resolution data. So if you want to fetch big brain, for example, if you want to have big brain or maps in the big brain, you definitely don't want to fetch the whole big brain right away. Yeah. So that's why we have two steps. We have the definition of a map, and we have this extra step of fetching. And for big brain, you would always want to fetch only a local region or a downscale version. We will see that in a minute. But that's why we have separated the steps of requesting the map and actually fetching image data. Are you fine? Is it
constellation?
Maybe so what I would do is I just fetch the puzzle, just get access to the parcellation. So just say parcellations.
We need to get the
and then
now that's the right postulation, because if you write on the postulation,
in this short form, I don't always need to write out this full Siibra spaces. I can always most of the functions you can just use keywords. Just as we saw in the beginning for the instance table, Siibra will automatically do that. So if it gets only a word, if we look at the instance table, if the instance table can translate this into an object. So when you use Siibra more often, you will use the short forms, the keywords. Yeah. So the full map, and then I would plotting plots. Usually plot right is a good function to do this. Sure. Map.
It goes. Yeah.
That's really cool. In fact, for those who are listening, there's actually a shorter form for all of this. So you can if you often use maps, you can there's a short form. I can right away instead of taking parcellation, I can say Siibra get map, and then I specify the parcellation. And space.
What you're doing is exactly.
This should also. Yeah. So this would be actually a short form for the digits. Siibra get map. And you could even have a short, you could even add here map type.
Oh, this is sorry.
Statistical to get realistic maps if they are this would I'm not sure if this works for the functional map though. But this is a short form to do this. Maybe before we move on to the next page, what we show you here is you don't have to figure that out yourself in real life. So we have, of course, documentation on read docs. That's a page. Which has much Python software documentation. So there is this page Siibra python.readthedocs.io. You can just check correct.
Yeah.
And this has documentation for Siibra. And here you have all of the things explained. Yeah? It also explains these concepts that I told you. And there's a step-by-step guide which has programming examples for most of what we are doing. So you find here categories. We are currently doing something with maps. Here's the category maps and templates. And you find here documented code examples. For example, finding reference spaces. Yeah, here you see really documentation of code. And this is working code. So this documentation automatically executes the code. So it's proven to work. And you can download these code examples here in Python notebooks. And it's all explained. This is not 100% complete yet, since we are still developing the library, but there is a lot already in the documentation. So you don't need me to tell you how this works. You will find that in the documentation if you want. All right. I will move on here at this stage. Before we go over to features, let's have a look at reference templates and the big brain. We are sitting here because we are interested in big brain a lot. So in the same way that we can fetch parcellation maps, we can fetch templates. So we could also fetch the M&I template, for example. But since big brain is also a reference space, and if we fetch the template for big brain, we get access to the big brain model, which has these high resolutions. So what we can do is we just access the big brain space, and then we get the template from the space. It's exactly the same way. We have the semantic thing, that's the reference space. Then we have this spatial thing, that's the template. And then we have, if we fetch from the spatial thing, we get the image. So it's the same thing here. We get the template from the big brain space, and then we fetch from the template, and we get a nifty image that we can display. Yeah? So when I execute these lines, I get a nifty image showing the big brain. If I don't tell fetch anything else, it will not download the complete big brain, of course. Yeah, this is really a 1 terabyte data set. You don't want to download this to your computer for many, many reasons. I'm not, so Siibra would also complain. So if you just call fetch, you get a lower resolution version, which does not mean that you cannot access high resolution. Yeah? But if so, if you look at the documentation here, if you press Shift Tab, it actually shows you also here documentation. You see, oh no, that's not. That's the documentation of the plotting method. I'm sorry. Just copy it over. So this fetch method here, it has also several parameters, and one possibility is here that you could specify resolution in millimeter to download higher resolution versions. Yeah? Usually, what you could do is you could press use -1 to say I want to have the highest resolution. Siibra will not do this. It will not download this 1 terabyte thing. It will complain. So if I do this, it will choose a lower resolution version, which is higher than the previous one, which it considers feasible, and it usually considers feasible for download what has a few hundred megabytes. Yeah, so you don't want to do this for the whole brain model, but I will show you a bit further below how you download high resolution chunks from the brain in a certain position. We can do that with the same method. I will show you in a minute. Yeah. So the fetch method also accepts other parameters, for example, specification of volumes of interest, and we will see this in a second. I'm very quickly returning to slides. So we have seen now how we fetch reference templates, how we access spaces. That's all not yet terribly interesting, but now I think it's getting interesting. In a typical workflow that you do in Python with Siibra, what you would often do is you would specify some form of location in the frame. For example, you come with some coordinates that you're interested in, or you probably have a threshold activation map from an fMRI image or something like this. You usually have something that tells you a location in the frame. Very often that's depicted here on the top. Yeah, so you often maybe you click somewhere, then you get a coordinate, or you have an image in a standard space which shows you some activations or things like this, or you have a whole list of coordinates, but usually you have something that tells you a location in the frame that you're interested in. And then to use the functionality in Siibra, what you usually want to do is you want to assign frame structures to these locations. So you want to say which frame regions are probably at these locations. And then you want to use either the locations or the related frame structure, frame regions, or both, to get information. Yeah? Get this access to multimodal data sets, maybe extract a chunk from BigBrain at that place, things like that. And we will exactly look into this workflow now. Yeah? What we have learned until now is basically the machinery we need to do that. So this is the next part in the notebook is doing this. We want to assign frame structures to locations. And what I'm doing here is I basically just create a point with a certain coordinate. This is just a random coordinate that I fetch. And I'm just doing this here with a string that has a millimeter sign, millimeter attached to it. There are different ways to use a point. But as always, if I just have some coordinates, Siibra wants me to tell in which space are these coordinates. Yeah? Siibra doesn't like you to just give it coordinates. It wants to know where are these coordinates in which space. So here I say this is a coordinate from the MNI 152 space, and I just create this point. One way to get such a point, one very easy way is to go back to the viewer. Yeah, you hear the viewer, and you could just use this thing here on the top that we are seeing, where you see a coordinate, right? So I could just copy this here. Yeah? Just use Control C to copy this, and that's how you could, for example, get to know such a location. So let me just do this. I'm copying in what I just had in the viewer. It's a different one, and that was in the MNI 152 space, right? So I create this point, and now I plot the Uniframe maximum probability map that we already have from some cells above, but I show the location of this point. So I should now, if you look at this, it should hopefully be where I am here as well. I think that's the case. There are also other ways, more sophisticated ways to get a location. And one interesting thing that we didn't look at, but which is quite interesting, especially to work in BigBrain, is let me just return to the BigBrain viewer. The viewer actually has an annotation mode. I haven't shown this to you, and that's not the topic of today, but here in the viewer on the right, you see plugins and tools. And there is an annotation mode. So when I select this annotation mode, I get here a simple side panel, which allows me, for example, to annotate points. Here's a point, I can click on this, and I can put this point somewhere in the BigBrain, for example, here in the occipital lobe. Yeah, I just put a point here, and you see it says at this point. I could give this point the name, something like this, doesn't matter. And there are more things I could do, but here's an export button. Yeah, so I can export this point, and here you see I get a larger text file that describes this point, which I can copy or download. I can here just copy that to the clipboard. Yeah, you see that here. When I copy this, this is in JSON format the specification of the point that I just clicked. And I can use this. I can use this format here. I just copied it directly in Python. So I can say Siibra from JSON. This generates an object from the JSON specification. And I just copy this in. But I just had to see this is quite complex, but it mostly defines these points, the units, and it also defines the coordinate spaces. Here's an identifier of the coordinate space. This is the identifier of the big brain space. And if I just execute this now, so I ask Siibra, please generate the point from this specification. And I look at this point. So I bring this point. And we say it's a point in the big brain at this location, right? So that's a different way of generating the coordinate. And I can also plot this point now here on the big brain model that we already fetched, and it should be this same location. Look at this here, hopefully this. Yeah, here's the point. That's it. Yeah. Well, so there are different ways to get exact points. Yeah? And now, as I said, it's really interesting to assign frame factor to this point. And this is very easy now with Siibra. So I just use this point here, which I have just constructed. And you know we still have this probability maps, these unit probability maps from a few cells above. And I can ask these probability maps to assign frame structure to that point. Yeah, so I can ask this particular parcellation map, which was in MNI 152 space, if you remember, to tell me where this point is. Now the point is in the big brain space, right? So, and I told you that Siibra is taking care of it. So when I execute this line, Siibra will actually recognize that this point is in big brain space. It will project the point to the MNI space, and then assign it to the regions in the unit probability maps. Let's do this. So it even tells it. It tells the coordinates are converted to big brain from the MNI space for the assignment. And what it tells me here is this first structure, which is the point. I could also pass more points. I get a table which tells me the point is at that location, and it is assigned to region V1 with this probability. Now, usually this list will be longer. And what this list actually is, so if I assign this into a variable, just run it again, and if we look at this variable, this is a data frame, a pandas data frame. If you don't work with Python so far, you will not know, but pandas is a very common library for data science in Python. And the pandas data frame is actually a very powerful structure that is in principle an Excel table. It's just like an Excel sheet. It has rows and columns and names, and you can do all sorts of it, sorts of stuff. You can filter it, sort it, compute averages of columns, all those kinds of things that you know from Excel or from other tools. In R, this is also very common in the language. So what you get for these assignments is such a data frame with this information, and the simple thing you can do is just look at this data frame. But you could, for example, also say to Excel and store this to an Excel file, yeah? Like then I would store those. I'm telling you this because much of what we will see in the following will produce such data frames. So when we, for example, search for neurotransmitter receptor densities, we will get such a data frame with neurotransmitter densities. When we search for Phoenix patterns, we will get such a data frame with Phoenix patterns. When we search for connectivity matrices, we will get such a data frame with connectivity matrices. Yeah? Sometimes we search, for example, for images, then we get an image. But very often we get such data frames. And these are common structures. Yeah. So this is the possibility to assign structure to points. We put here a U term, but maybe in the interest of time we could also step away it My idea was that you also go to the viewer, select a point, and do that yourself. But I think we can also move on. I think, yeah, would you like to do it yourself or move on? Who wants to try it? We are moving on, yeah. So you saw how that works. A different way of specifying locations could be an image which has some peaks and blocks, such as a thresholded activation map. And with this notebook, we have an example, such an example image shipped with it. So we can just load this Nifty image here in the next cell, which gives us here such a few blocks in the brain where something happened. These here have actually been constructed artificially from a probabilistic atlas, but not from the Unity atlas. But you could imagine anything. Yeah? It could be any fMRI activation map or a threshold PET image or something like that. Of course, we also want to use such images to assign locations. And this works really exactly the same way. So if I have such an image, I just loaded this image, I can do the exact same call. I use the Winterschool probability maps. I could also use different oscillating map. And I call the same function assign, but now I don't pass over a point, I pass this image. Yeah. And what the system will be doing, it will assign, it will first look, are there different signals in the image that I can split? So it will split this into 2 or 3 different structures, and then it will assign it. So let me just do that here. And usually you see this already, you find 3, 4, 5 different structures in this image. And assigns them, and I get such a table. Now the table has more information. It's actually, just show this, if I don't filter it, or if I just show the full table, that's a long one, you see here. So it has the first structure, since it's a large one, has some relationships with many, many different brain regions. Yeah? Only the first structure that it's all in the image. And it shows us the values, that's the average value in the probability map of each region, but it also gives us now more information that it could not compute for points. It computes correlations of this plot in the image with each brain region, intersection over union. This is a containedness score. It tells us how likely this structure is contained in the other one. I don't want to go into too much detail here, but if we have now more information. What I'm doing here above is, since this is a lot, I just use functionality from these under data frames to say, just give me the rows where the correlation is larger than 0.3, which should be significant. And then also sort them by the containedness score. This is just arbitrary. And then I just get these 4 lines, yeah? So which don't even include all the structures. It includes 4 of the 5 structures. So it says the structure number 3 it has a significant correlation with V1 in the left hemisphere. And the structure number 1 has an even stronger correlation with IFG in the left hemisphere, and so on. Yeah? So this maps brain regions, in this case from Unity brain atlas, to certain images, to structures encoded in certain images. Okay. At this point, I'm moving on here a little bit. So what we have done now is we have input locations. We have seen different ways of inputting locations, specifying locations in the brain, and we have seen how we can enrich these locations with information about brain structure at these places. So at this stage, we have both the location and we have a set for each location, possibly a set of brain structure that are related to these locations. And this is now the basis for accessing all these multimodal data features that we just clicked in the viewer, right? So I can use this information now to get access to these different features, and we will look at this as a last thing today. We can look at quite a few of them, or do a break in between. What is your what do you think? Do we need a break at this stage? Let's do 1 or 2 features that we do break then. Yeah. I will just take a few more minutes and we will break later on. So the next section is now really for accessing features, and we will see in a minute how that works. So Siibra has a module that is called features, and it provides access to different forms of features. This slide is not very important for you, but it shows you a tree of the types of features that Siibra currently supports. So you see there are called the profiles, cell density profiles, receptor density profiles, big brain staining intensity profiles. There are features with tabular data. These are layer-wise cell densities, layer-wise big brain intensities, receptor density fingerprints. I think you saw those fingerprints. There is also tabular data in a way. Gene expressions from the brain. So we can use what we have seen query brain as for gene expressions. There's connectivity, oscillation, average connectivity. There are these e-brains data features. This is what we saw in the viewer, basically the rest of it. These data sets that are linked to brain structures which are not further supported because they are so diverse. And this here is the last small thing, but it's actually a very notable feature. We can query for volumes of interest. And this is what gives us access to high resolution data. So yeah, we are in the process of anchoring high resolution data sets to the big brain, sections or results from histological experiments, the deposited tissue, and we try to link those to the big brain model or to a different reference space, and Siibra allows us to serve those. We don't have terribly many of them currently, but we have a nice range of 1 micron resolution sections in the big brain, which you can discover in this way. We will look into this now. But let's start with the neurotransmitter receptors. That's a simple and intuitive example, and it also connects nicely to Nicolas' presentation. So the way that you would find regional neurotransmitter receptors is basically you select a brain region that you're interested in, and you ask Siibra to look for receptor densities in that brain region, right? That's what you do. So first thing is we get a region. We learn this at the beginning how this works. So I'm here using the left primary visual cortex from unit brain because I already know that the receptor densities have been linked to unit brain. And then there is a simple call which we will use for any type of query for data. Siibra features.get. Now that's the function that gives us multimodal data features, and it usually gets 2 parameters. The first parameter is the where or what. So in this case, it's my brain region, V1. Yeah? So I just put in this region, and then which types of features. Yeah? And here I just specify something from the list that you see here. And this can be done with auto-completion, just as we did it for the population and so on. So I can just write Siibra.features. Features, and then I can, for example, for the receptors, I say molecular features. That's what you see here, and oh no, it doesn't show it here. Molecular, and then you see here receptor. I think I want to show fingerprints here. Yeah? So then I get a list of features. There might be several. In that case, I will usually get 1. And then what I'm doing here, I just get the first one from the list and show the data associated with that feature. So you see here, I get a table with the mean and standard deviations of the receptor, neurotransmitter receptor densities for these different receptors. Now, so it's as easy as this. If I want to search for receptor fingerprints in different regions, I just put a different brain region here. I could also take regions that are further, that are higher up in the brain region hierarchy, and I might find more of them. So if instead of specifying 1, I could here say which brain get region, and I say, for example, occipital. this would actually translate to the occipital lobe, I guess. And of course, then I would get more features. And the first one is certainly, so this is now the one of E2. Yeah? But these features here are no more than one. We see it in the occipital lobe is now five different ones. The first one is the one in HEC. But the idea, and we will see different data modalities now, but it works always the same way. I get features given a certain anatomic concept and a certain feature modality, and then it searches. Okay. The data in this feature is, in most cases, if it's not images, then it's mostly always such a data frame. Usually a table that you get that you could store in an Excel file or whatnot with some measurements. All right. So my plan is to just take, well, let's say maybe 50 minutes more with you to see a bit more which kind of features you can access here. So we have just looked into neurotransmitter receptors that you can search here given the brain region. And we went a bit deeper already in the break into this, but basically what you get is a data frame with these measures, and all the features can usually plot themselves. So you see here also a plot of this, and these values correspond to what we have already seen in the viewer. If we had selected the same brain region, so you remember that we so if we select here area V1 as well, that's area 2, sorry, and we look here at the regional features, that's exactly the same data set that you see here, and you should also see the same values popping up in the side panel, since it's under the hood, the same software running here. Yeah? So these means and standard deviations, that's also what you get here. And I think you should also be able maybe to get a polar plot here. That's system can even do that. Well, I leave it there, but you just get the same data really. One thing that I wanted to note is when we do this query for regional features, the system has to do a matching, and this matching could be exact or inexact. And this is really very important information. Yeah? So if you, for example, find neurotransmitter receptor densities that refer only to a part of the region that you have queried. Yeah? For example, if I also search here for the complete occipital lobe, yeah, and if I get the receptor density of V1 as a match to the complete occipital lobe, you should probably know about it. You should probably know that this density applies only to a part of the region that you queried, as opposed to it applies to exactly that region, right? And actually, Siibra is doing that in the background. So once we have extracted a feature, we actually access this information from the matching process. This is here one way is to call this attribute last match description. So if we call this, let me just do that again because we messed it up in the break. So I do this again for V1 left. And if I then look here at the last match result, V1. So we were querying for V1 answer. We changed this in the break. Yeah, so now we have queried for V1. And if I then look at the last match description of this feature, it says actually area HSC1 to which the feature is linked contains area HSC1 left to which the region. So I see here that it's actually contained. Yeah, this gives me additional information to interpret what has been done. Yeah, if I search here for V1 in the left and right hemisphere, both of them, then it will show me an exact match. And sometimes it coincides really with the same region. It has been linked to the same region. And here you will sometimes find much more complex information. It will sometimes say, I match this to the region, to the map of region X in a different space, since I have to map it to a different space. You will read that here, you will see that. this information. So you can really understand how the link between the data feature and the brain structure was found. I'm not going into much detail now. So in the break, someone already asked, can I also do a genius patents? Yes, we can, and it works the same way. Yeah? So we can put V1 again in here, but this time here for different type of feature image patents. And in that case, we also have to specify candidate genes. So if I would just call it the same way, Siibra will complain. It will just tell me you have to specify a gene. I get an error, but then I can specify one gene or list of candidate genes. And then I again get a table structure with the genes specified from the brain atlas found for these brain regions. If I plot them, it just shows me such here a box plot with for the Z scores for the levels. Sorry, for the levels. But what I also get is again such a tabular structure here with all these measurements for this brain region. In this particular case, this was a query based on the coordinates of the tissue blocks of the atlas, and I can also get access to these positions and just visualize where these locations were. And you see they are really here in the in V1. I think if I repeat this, I should see them in both hemispheres, since this query was in both hemispheres. Yeah, you see here results from V1 in both hemispheres. It also works the same way for connectivity. In this case, I do not pass over a region, but a parcellation for the query, since the connectivity matrices are related to the parcellations, not to particular regions. But otherwise, this works the same way. So I'm querying here for streamline bound features and just take the first one again from the list that was returned, and it has some information. It shows me that this first feature is from the HCP cohort, and it has information of these 200 subjects. You remember this also from the viewer, we saw that in the viewer as well. And I can then get the matrix for any of those subjects or the average matrix here just by saying get this matrix. And again, this is such a data frame. Yeah. In this case, it's actually connectivity matrix, so the columns and rows correspond to brain regions. But the structure is the same. I could store this in an Excel table or a CSV file, whatever I like. I can also, like the other features, I can also do a plot. Here I'm doing a log scale plot of the matrix. This is of course a bit much, since we have here 300 regions to read here in the notebook, but it works the same way. I can also visualize the connector on the brain by computing the centroids for this for the regions corresponding to this connectivity matrix. And we saw that at the very beginning, when I want to compute centroids, I have to tell Siibra which space, and I want to do it in the MNI152 space here again. So I just compute them, and then I can use another plotting function from mylearn to visualize this. It's here. So the computation of the centroids takes a little bit. It's doing that on request, and so I can now show here this connectivity in such a connector. All right. So different types of features that I can query with always the same pattern. Now, as a last thing, I want to show you how we can actually work with big brain data. I promised this from the beginning, so let's do that now. The first thing I told you is we can extract image information from the big brain 3D model at higher resolutions. Previously, we fetched template, but it fetched it at a low resolution for the big brain. Of course, you might be interested to fetch a block from the big brain at the full resolution of 20 micrometers. And you can do this by specifying the resolution you're interested in and making the query more precise, that the resulting volume gets smaller. Yeah? And one way to do this is to specify a bounding box in the big brain space. So what I'm doing here is I just specify a bounding box that is spanned by two coordinates in a very same way as I specified points previously. Yeah? So Siibra allows me to construct such bounding boxes, and then I can again do call the fetch method in the big brain template that I already used earlier without any arguments. But now I pass this volume of interest. Yeah, so this bounding box, I call this VOI, volume of interest. I could give it any name. I could also call it TIMO. Yeah, the point is this is a bounding box in big brain spanned by these 2 points, and I just took them randomly in this case here. And now I fetch by specifying this volume of interest. So the fetch method knows, okay, I don't have to download the whole brain. I just have to download this region of interest. And now I can use this resolution parameter that I already mentioned earlier and say, I want to have it at 20 microns. And then Siibra will do it because it recognizes that this volume of interest specification is a small thing. It's a really small thing, so that it becomes feasible. And then I can plot this chunk. So if you run this, so it fetch now the volume of interest from big brain between those 2 points. And this is again a nifty image. Yeah, as always, this is a nifty image which contains the high resolution information from the big brain state. And I could use anything, any volume of interest. I can also compute the bounding box over a brain region. For example, in the MNI space, yeah, I could fetch a region from Unity plane or from a Desikan atlas, get that bounding box, and fetch with that bounding box. Siibra would then automatically translate the bounding box from the MNI to the big brain space and fetch. Yeah? So this way, you can easily download a block from the big brain for a particular brain region. Yeah, in the 2 lines of code.
Can it also be an ROI to any shape, or it has to be a cube?
It certainly does it with bounding boxes. Yeah, it's you can also extract for shapes, but this would require some additional steps. The fetching is always in rectangular structures. Yeah, then you can on top of this mask things out. That's possible. Yeah, but it always goes in cubes. Yeah, well, they need not be square peg. Yeah. But anything. Good. This is one way to access information from the big brain. Yeah. So just to let you know, this is the arbitrary bounding box. You could again click in the viewer to get some points, but I can also do things. You know, I have this region V1, for example, from the top, and I could. Well, it's very large, yeah. But I could say Unity brain get region HOC5 left. It's, for example, a smaller one. Yeah. That's like this. And then I can say get bounding box. Yeah. And guess what Siibra wants to know if I want to get the bounding box of the region? It wants to know the space, right? So in which space? Yeah, and I could then say I have 52 space, for example, and then I get a bounding box, and then I have 52 space. Yeah, and if I then would fetch, I would then use this method here. Fetch from this bounding box, and it should actually work, and it should work. It does not work. Okay. This one ranges outside the brain. It was a bad example, but I'm sure that works. Oh, that case it works. So what I can do is I did now explicitly walk the bounding box from MNI to big brain, and it can use this now to fetch big brain data. This might still take a bit. I'm not exactly sure how large the bounding box of HOC5 is, so it might take a little bit. I mean, now we are really downloading data. But there are different ways to specify bounding boxes, and you can use them to fetch from the big brain mode. Another way to request big brain information is to fetch cortical profiles. These are just features. Yeah, these are just this is just another type of features. Big brain intensity profiles. What we're doing is we are providing pre-computed stable profiles that Conrad Axel has extracted from one hemisphere of the big brain. You could actually also extract such profiles directly with Siibra, but these are predefined ones. And this takes a bit at the beginning because we are downloading there as a full file, all of those profiles at the beginning, but it will then automatically filter them by region. Yeah. So this is another way of getting access to big brain data by requesting cortical staining profiles to big brain. As I said, I'm here on the Wi-Fi, so everything that downloads data is really on my machine, so I'm not on the cable network. And I'm also not in the cloud as you are. Yeah, I'm running this on my local machine, so it's really going to the Wi-Fi. But you see, it has now fetched 163,000 profiles, and it's filtering them by this region area 4P that I have specified here, and then I have 567 of those profiles which are likely in that region. Does it know this for the way it should actually work? I don't know why it's not working. Yeah, so yeah, just for one of them, you see here the cortical staining profiles. It is tagged with the cortical depth, with the cortical layers. So this information is in the data feature, and we have 500 of those for the brain region with which we are. If I don't plot it, if I look at the data, you will see that this is also just a data, actually a series of values along the cortical depth, but it's also a pandas data structure. That's not the brain, it's a series. Yeah? So the cortical profiles, since that's a one-dimensional data set. The last thing is 1 micron sections. So I can also find 1 micron sections of big brain and fetch information from those 1 micron sections. And we have a few hundred of those 1 micron sections available for big brain. You can also see them in the viewer and find them online as a data set. But Siibra can actually find sections that intersect with brain structures. So what I'm doing here is I'm instantiating region A55. Here in the left hemisphere, and then I run a feature query for this region with the feature type volume of interest. And the way we have currently modeled this is that the ticket section is also a volume of interest. It's just a very thin one, but it's a volume of interest. So it will find volumes of interest that intersect with this brain region. Now, so if we run this and then I bring this here, so you see that it has here 1, 2, 3, 5, 4, 1, 2, 3, 4, 5, 8 sections that intersect with that region. These are the section numbers. And for any of those, I can access the 1 micron resolution. Yeah, so these are really huge images in the cloud with 1 micrometer resolution, the whole brain segments. And you see here the third one. The third feature is, oh, that's not the fourth feature, is section 1400. So I'm using this here, so the number 3 is the fourth feature. And then I just fetch the image as I did it for the big brain. I just fetch this section and display it. And again, what's happening is if I fetch the whole section, it will just give me a lower resolution representation since it's really huge. Yeah? If I want to, and you see this here on the left, I show it in the 3D context. This is the plane where the section is, and here in the coronal plane, you see the section, but a lower resolution version. And I can now do the same thing as previously. I can specify a bounding box for inside this, this section, and then download higher resolution information from the section. We are doing it here. So this is a bit crazy, but I try to guide you through it. So since we found this section as intersecting with area H65, right? I will now try to extract a piece of 1 micron data that is inside this area H65. which is of course not a complete section. So what I'm doing here is I get the bounding box of area HOC5, the left hemisphere, in the big plane space. We did this also with these cells, right? I have a region, and I say, please give me complete the bounding box in that space of yourself. This is a three-dimensional bounding box. And I know from my theory that the brain section intersects with this bounding box. Yeah? That's how I found the brain section 1402. But I want to extract a piece of this brain section. So I now intersect the 3D bounding box of area HSI with the bounding box of that image to get the thin bounding box that applies to the image. Yeah? So I first take the bounding box of HOC5L, that's a block. Then I intersect this with the bounding box of this 2D image, which is section. Has also a bounding box, but it is very thin. The section is only 20 micron thick. Yeah? And then I get a bounding box that is very thin and small. Yeah? And this bounding box, I can use it again for fetching. Yeah? It is still quite large. So what I do here, I zoom this bounding box to a 10 degree size. I make it even a bit smaller. Then I should be somewhere in the middle of HSC5 in that section. And this volume of interest, this bounding box, I use this for fetching. Yeah? And I fetch at a resolution -1, which means the highest possible resolution. Let's see if I can find it. And if I do that, I'm running it here, but you already see it here on the bottom. I get really a patch on my micron section at the full non-micron resolution. Yeah? Which should be inside area HSC5. You get the idea, this is a bit of geometry, right? But if you want to navigate in the huge 3D data, that is quite tricky actually. So you have to do such a thing. Yeah? We find a section that intersects with a certain structure, and then to get information from that section, we intersect the bounding box of that structure with a section. This gives us then something two-dimensional, and then we can get it from the air. Yeah? And if you would do that with a 3D board, so we have also some 3D tissue block anchor, it works the same way. Yeah? So the 2D section is also a 3D volume with 20 micron thickness, so very, very thin. We perceive it as something two-dimensional, but it's actually three-dimensional. Yeah? The tissue section is 20 micron thick. So if we have a tissue block, we have also some blocks from polarized light imaging here. It works exactly the same way. Yeah, you can do exactly the same way. You can find intersections and download from the data. Okay, I think one final remark. Whenever we download such pieces of images, yeah, so we have now really downloaded a tiny piece of a 2D section, which is a rather small image as you see here. Since these are returned as nifty image objects, that's not just an array of pixels. It also has metadata. And the most important metadata in this case is that attached to the image is a transformation matrix that knows how the image is related to its reference space. Yeah? The reference space in that case is the big brain space. So with the small image that we get, we produce automatically a transformation matrix that knows where this image belongs in the complete big brain. Yeah? And that is why, in the last cell here, I can actually plot the same image. I'm plotting here crop, and crop is nothing but that image here. Yeah? I just gave it the name crop. Nothing else but this image. I can just plot this image and the big brain template in the background. And as you know, when I fetch the big brain template without any further arguments, it fetches a low resolution representation. Yeah? So I have a low resolution version of the whole big brain. I have this little piece of image at a very high resolution, but since they know their transformations to the reference space, I can plot them together at the appropriate place. So it plots here exactly this small crop. It's so small you don't see it, but it plots it exactly at the position where it belongs. Yeah? So we have orders of magnitude in image resolution here, but there is still a clear, well-defined relationship where it belongs. Yeah? And we could even overlay the 1 micron pixels with the 1 millimeter boxes with low resolution brain. Yeah? So even if we extract stuff, the data structure still knows where it belongs. Yeah. Good. that's the end of this Jupyter notebook here. It's probably wasn't a lot, I see that in your faces, but I really try to give you a quick tour. In previous workshops, we usually didn't go much into Python. We did more in the viewer and did some analysis and compared the sector distribution in the different regions and looked at that. It was really the idea for this tutorial today to go into Python a bit more depth, because in the past, some people really asked for it. And I hope, at least for some of you, that this was more interesting and you see the potential of using this for doing reproducible workflows with atlases, training regions, big data. Just as a final remark, this is all still in development. So when you saw at the very top here, at the very top of this tutorial, you see it's still a version 0 point something. Yeah, so we do not claim that there are no bugs, and there will be more features coming, and we will probably also change a few things and optimize it further. But it should be sufficiently usable already for many things. So we are using it a lot, and other people, collaborators with it as well. So, and it's all out there in the public. So you see these notebooks are public, software is public for installation, documentation is public. That's all there. And if you use it and you have questions, just get in touch with us, and we will be very happy. Yeah, but one way to get in touch is, by the way, the forum, the Big Bang project. That's a good place to ask. So many of the Canadian friends are around, and we are around, and that's also a good place to get in touch. Okay, thanks a lot.